And we're back. Sorry about that very quick exit. The screencasting stops at exactly 15 minutes. So I was like, oh my God, it's stopping. Okay, but we are back. So this is where we ended talking about some D-ketoses. All right, so now let's look at our sort of chain of D-aldehoses. All right, so the aldehose, again, the difference here, right, is that we're only going to have, remember, the R group on one side, not on both sides, okay? So the configuration determined, again, is exactly the same way. Everything's the same. Yellow is going to be new. B is the most, or the blue is the most common, right? And pink is going to be the highest numbered asymmetric carbon. Okay, so again, D, because we're going 1, 2, 3, so clockwise, but again, hydrogen pointing forwards, so that flips that. So this is D-glyceraldehyde. And again, you see the same splitting pattern, right? You add another one, you get two options. You add another carbon backbone, you get two options, right? In every single case, two options all the way around, okay? So what are the most common ones? You've got glucose, which is a hexose. You've got mannose, which is a hexose. You got lactose, which is a hexose. And then you've got ribose. I'm sure you've heard about ribose before, ribose sugars in biology, right? So that's a pentose. And you have erythrose, which is a tetrose, right? And then glyceraldehyde is your triose. Okay, so then if this looks so similar, what's the major difference between these aldoses and ketoses? So let's go back. Again, this is a keto functional group, right? So there is something happening here on the other side of this C double bond O. Whereas if we go to the aldehose, your C double bond O is hidden sort of in this CHO, and then the only thing that's attached to it is a hydrogen. So basically, you're starting, the way the sugar is drawn, it's drawn differently. So if it's an aldose, then the sort of one position is going to be a CHO. If it's a ketose, the one position is going to be a CH2OH. Okay, that's the major difference. You just look at the one position, and that's going to tell you right off the bat what it is, if it is an aldose or a ketose. Okay, so let's talk about some other sort of nomenclatures and stuff. All right, so stereoisomers that are mirror images of each other, we call them enantiomers. Okay, enantiomers. So, and these molecules, some of them can possess two or more chiral centers. So there may be multiple stereoisomers that can exist. Okay, but stereoisomers that are mirror images of each other we call enantiomers. Now, what about if it's not an exact mirror image? So what about if we have a pair of isomers that have opposite configurations at one or more chiral centers, but they're not mirror images? So we've got opposite configurations, but they're not mirror images. Then these are diastereomers. Okay, so any two sugars in a row from the previous two figures. So let's go back. These are diastereomers. These are diastereomers. These are diastereomers. Okay, all of those are examples of diastereomers. Whoop, going the wrong way. Okay, what about epimers? All right, epimers are two sugars that differ in configuration at only one chiral center. So let's go back. Differ at only one chiral center. So look at mannose here, all right? And what did the previous slide say to compare it to talose? So let's look at mannose. And then let's look at talose. Talose is over here. So same in position 1, same in position 2. 3 is the same. 4 differs. That's it. 5, 6, exactly the same. They only differ in one position. These are epimers. Okay? All right. And I know I'm not really getting into enantiomers, but that's because we've already talked about enantiomers. And enantiomers are kind of hard to determine from a Fisher projection, okay? And again, since I didn't require you guys to take organic chemistry before we get into this class, there's a limit as to what I expect from you, okay? But diastereomers and epimers are quite easy to identify based off of pictures. So those are the ones I'm going to be able to ask you about. Now, I know the definition of what an enantiomer is, but not necessarily going to ask you to identify one for me. All right, so let's talk about what happens when these things cyclize. All right, so alcohols react very readily with aldehydes to form the hemiacetal, okay? So here's your alcohol right here, and the sort of lone pairs on the oxygen are going to interact with the carbon. This hydrogen is going to move over here to this oxygen, and you end up with this brand new compound, okay? So this is your hemiacetal. So then let's look at how that relates to over here. So we have our D-glucose, okay? And how this cyclizes is 6 is going to attack at the essentially the, so your 6 is up here. So the 6 isn't the one doing the attacking. This functional group on 5, so this is going to attack at the 1 position. So 5 attacks 1, and then we get this sort of 6-membered ring, which is very similar to purine, okay? Purine is a 6-membered ring in which one of the options isn't a carbon, it's an oxygen. And so what we say is that the cyclic form of glucose is pyranose. So it's a sugar form, okay? So this is pyranose. And why did I originally talk about alcohols wanting to react with aldehydes? Well, that's because that's exactly what happens in this structure. So this is your alcohol. Sorry about that. This is your alcohol, and it is reacting with the aldehyde. So that is the reaction that happens in glucose to generate the cyclic form. Okay. And then this is a way in which, and we'll talk about the different ways to draw these. So this is an example of a Haworth projection of glycopyranose. This is an example of a Fisher projection of glycopyranose. Also notice again that we've got some other weird stuff going on, alpha and beta. I promise we're going to come back to this and talk about all these things. Okay, right now I'm just talking about how it cyclizes. So again, how does it cyclize? The alcohol at position 5, this OH group, attacks the carbon on the aldehyde. So 5 attacks 1. All right, so that's glucose. What about fructose? Fructose is also a 6-membered ring, or sorry, also a hexose, but fructose, unlike glucose, it looks a little different, right? So glucose is an aldehyde, but fructose is sort of a ketone functionality, okay? So it's going to interact differently than glucose did. And it doesn't form a 6-membered ring, it actually forms a 5-membered ring. How? How is it doing this? Well, again, the alcohol here at the 5th position, the alcohol here at the 5th position is going to interact with the ketone, with the carbon. So 5 interacts with 2. And since 5 is no longer interacting with 1, we're not going to get a 6-membered ring. We're going to get a 5-membered ring. And so what we see is this is furan, and it looks very similar. So we refer to the cyclic forms of fructose as furanose, okay, or fructofuranose, okay? And again, we've got this alpha and beta thing going on. We're going to talk about that. We're going to talk about the difference between how to draw these out in Haworth projections versus Fisher projections, okay? All right. Now, okay. So also, I didn't mention the difference, right? But when alcohol attacks a ketone, you get hemiketal instead of hemiacetal. Okay, but they're very similar structures. Okay, so here's your hemiacetal, and then your hemiketal. Again, the only difference is it's RR, okay, instead of RH. So when these are formed, basically the carbonyl atom becomes an asymmetric center. Okay, so isomers of these monosaccharides that differ only in their configuration about that asymmetric carbon are called anomers. I know we got a lot of words that sound similar, and I'm sorry, guys, but just sort of studying will help you, but these are anomers. And so we have alpha and beta anomers. Okay, so let's look at what we got here. So when the hydroxyl group at the anomeric carbon is on the same side of the Fisher projection as the oxygen atom at the highest numbered asymmetric carbon, the configuration is going to be alpha. So let's read this. Let's say this again. When the hydroxyl group at the anomeric carbon is on the same side of the Fisher projection as the oxygen atom at the highest numbered asymmetric carbon. So let's go back. Okay, so we're going back and we're going to look at basically what's happening here. Now, if you look, we haven't talked about Haworth projections. There's no way for you to even determine what the heck I'm talking about right now with alpha versus beta. Okay, so let's look at the Fisher projections, which is something we're a little bit more familiar with, okay? So it's when the oxygen is on the same side as the highest number carbon, which will be the carbon at the top in the Fisher projection. So hydroxide's on the right, the oxygen's on the right. This is alpha. For here, glucopyranose, it's beta because the oxygen's on the right, but the hydroxide is on the left. Now, how does that relate to the Haworth projections? Well, alpha means the hydroxide is pointed down, okay? So same side would mean it's pointed down in the Haworth projection, or opposite sides means this hydroxide is pointed up. Let's go back and let's look at fructose, okay? So here we have our fructose structure. So again, oxygen, hydroxide, same side, this is alpha. Oxygen, hydroxide, opposite sides, beta. And again, if the hydroxide is pointed down in the Haworth projection, it's alpha. If the hydroxide is pointed up in the Haworth projection, it's beta. Okay, and we're going to talk about this stuff more coming up, so don't worry too much if you're like, wait, what? We're going to talk about Haworth and Fisher projections more. All right, so this is going to be the end of, yeah, we'll come to this in the next video. So this is the end of this video because we're starting to run out of time. This is not the end of lecture, right? This is the end of video number 2. Make sure you click on to watch video number 3.